the sum of digits function that we saw in the last lesson, now here it is, seems to be very natural. So natural, it's hard to imagine another way to do it. But in fact, this intuition is wrong, completely wrong. There is a second approach to write the function, a quite different approach that leads to another and in fact much better definition. To introduce this approach, let's start with a simpler function, the factorial. This way we can focus on the key idea, and after we write the factorial function, we'll get back to sum of digits. So factorial function, let me give the mathematical definition. 0 factorial is equal to 1. N factorial is equal to n times n minus 1 factorial when n is greater than 0. So this is the mathematical definition. There's nothing about programming or programming languages in this definition. It's purely mathematical. This is called the specification of the function, the mathematical definition of what it calculates. We can now make a first definition by following this specification exactly. So I define fact1 of n. If n is equal to 0, then 1, following the definition, else n times fact of n minus 1. There. Now let me take this and feed it using a keyboard command. Oops, I made a mistake. Do you see what the mistake is? It's a very common mistake. In fact, the recursive call is not the same name, fact1. Let me define it again. Browse fact1 of, let's say, factorial 10. This gives 3,628,800. This is factorial 10. This first implementation actually is very similar to the sum of digits implementation we saw. It follows the same approach. Now let's introduce the second approach. The second approach uses an idea that I like to call the principle of communicating vases. Let me bring in a diagram to show this. So the approach is as follows. We start by inventing a formula that splits the work we have to do to calculate the factorial into two parts. So here we have n factorial equal I factorial times a. So n factorial is the number we want to calculate. I and a are two new variables we introduce. And when we start the calculation, we don't know anything yet. We start with I is equal to n and a is equal to 1. Okay, n factorial times 1 is n factorial. Then the idea is to decrease I and increase a together in one step, all while keeping the formula true. So we keep doing this, and eventually when I becomes equal to 0, then we have here a 0 factorial, which is equal to 1, and therefore a must be equal to n factorial, so a is the result. Okay? So here's an example. When n is equal to 4, we start here at the beginning. 4 factorial is equal to 4 factorial times 1. So I is equal to 4 and a is equal to 1. Now we decrease I by 1 from 4 to 3. And we have divided it by 4 in doing that. So we have to bring back the 4 somehow. So we multiply the a by 4 from 1 to 4. And then we continue. We decrease the I from 3 to 2. So we've divided by 3. We have to multiply the a by 3. 4 times 3 is 12. We continue 2 to 1. 12 times 2 is 24. 1 to 0. So 24 times 1 is 24. And the result is 24. Okay? Now, in order to make a program with this principle, let's see if we can make a general case where it's true for all possible values. So I start with I factorial times a. And now I decrease I by 1 times a, but I've divided by I, so I have to bring in an I here, times a. And this gives me I minus 1 factorial times I times a. So if we look carefully, we can see there's actually a new I, which I call I prime, which is equal to I minus 1, and a new a, which I call a prime, which is I times a. With this, we can now make a second implementation. So fact2. And now the I and the A become arguments. And we start by the end case. If I is equal to 0, then the result is A. Otherwise, and now we have to do the step where we decrease I and we increase A. So I minus 1 and I times A. So there, this gives us our second definition. So let me feed this definition to the system. And now let me do the calculation. Note that we have to give two arguments. So the initial I, which is the 10 that we want to calculate, and an initial 1 for the A. And now we calculate this. Let me move the diagram out of the way. We've seen here a second result, 300,628,800. So this, again, is the factorial of 10. Now you notice that we have here two quite different looking definitions that are calculating the same function. The second definition, which is using the principle of communicating vases, is also something which I call the invariant programming style. So which, since it's based on an invariant, this formula, n factorial equal I factorial times A, which we keep true. So this formula acts like a motor. It pushes the calculation. So as long as the formula stays true, we can push the values of some of the variables in the formula to the direction we want, and the other values will calculate the result. So with this idea, we can actually calculate the factorial, and we'll see that this is actually a much more efficient definition.